This is a really good one. Really interesting one because it's good science, I think. It appeals to some papers we wrote and talks about a really industrially relevant problem, particularly in the areas of process scale up, bioprocess design, etc. So I'm kind of excited to share this. We're talking about interfacial mass transfer, in particular, mass transfer across free surfaces in agitated, sloshing, shaker flask systems and whatnot. And why this matters is that a lot of processes are developed at lab scale where we may not have sparging. We may just have a shaker flask. We may just have some sort of small vessel where we get a lot of interfacial transport. Second of all, there are good guides in the literature, and I'll speak to this, guides that speak to what KLA, for example, should be at different operating scales and conditions, but they sometimes can be adulterated a bit by headspace incursion that the operators or authors may not have appreciated at the time when writing their scale-up rules. I'll speak to that as well at the end with a little bit of a case study and an actual demonstration where this comes through. So again, the big picture is this. We're talking about systems where an oxygen has a few ways, or any dissolved gas has a few ways of getting in the system. Option one is via the free surface, where we have some sort of concentration maintained in a headspace, and just due to the agitation of the fluid and the convective transport processes, which I'll speak to today, along this free surface, we can whisk oxygen or other gases from the headspace into the aqueous phase via convection at the free surface, okay? In a non-sparged system, this is the means by which dissolved gases get into the aqueous phase. And so foundationally, this is a transport mechanism that's relevant in systems where we don't have sparged gases. Now, when we sparge gas into the system, we have another oxygen or dissolved gas transport mechanism. We have KL and individual mass transport processes going on around each individual bubble. These are also pouring dissolved oxygen into the batch here. So we have two paths. One is the headspace and transfer via the interface. One is the sparged gas. And now, if an oxygen molecule arrives in this fluid, we might have a hard time discovering which path it came through. So we just have a probe stuck inside this vessel and it's measuring the time evolution of the DO concentration, trying to figure out what the effect of KLA or HLA might have been if we have both physics present, particularly if we have headspace present in tandem with sparged gases. What our probe is measuring is going to be a mixture of the net effect of those two individual transport processes. So when we're characterizing KLA or trying to measure KLA, as it were, we've got to make sure that we're contextualizing, understanding, and scoping any free surface transport that might exist inside the system. Because what we actually think KLA is in a small scale or what we think the effective mass transfer rate was in a small scale may not have been what we're realizing at the larger scale due to the depressed effects of the free surface at larger scale as this volume becomes bigger. We'll speak of this in detail, but this is the big picture. There are multiple ways in which oxygen or CO2 can intrude into an aqueous phase. We're going to tease those apart today and understand how we can attack this problem at different scales. The small picture is this. A lot of these systems begin with these shaker type systems. You know, if we've got some sort of rocking table, we've got some sort of shaking table, we've got some sort of orbital shake, as it were. The only means by which we're going to get oxygen into the system absent sparging is through headspace transfer, okay? And so we've got to come up with reliable ways to characterize this, not only to help with scale up in bioreactors, but also understand what we're going to get in this vessel, as it were, as we undergo these kind of not non-traditional, but certainly non-sparged gas type oxygen transfer mechanisms. We've got to have good strategies for bridging free surface transfer in these different types of systems. I'm going to be speaking to, with that kind of teeing that up, a little bit of a theoretical introduction, how we might approach these things. I'll talk about production vessels, lab scope vessels, and do a working demo. So again, the agenda slide, I don't think a good talk needs an agenda slide, but nonetheless, there it is. There's our roadmap where we're going today. Okay, I'm speaking to a couple of papers we published in the past couple of years. One was on free surface transfer in lab scale devices. These are shaker flasks, little wells, tiny bioreactors, etc. This is available in Chemical Engineering Communications. We followed this up with another report in actual bioreactors in a high turn-down environment. So where we had only a partially filled, say, XTR 200 or partially filled XTR 2000, where we have a lot of free surface relative to the volume of the fluid, and headspace transfer becomes relevant. We want to characterize and attack and understand what sort of transport mechanisms we're seeing in those types of processes as well, where the free surface matters. because the free surface to volume is small compared to a totally filled vessel. Okay, so what does this look like in the code, and what does it look like from a modeling perspective? There are two paradigms by which oxygen can enter the system, and I'm going to introduce two separate transport coefficients to discriminate the two. First, it's very familiar, KLA. KLA is describing a volumetric mass transfer coefficient. It can be thought of as occurring on a bubble-by-bubble basis. Said again, the total mass transfer into this aqueous phase is going to be the sum of the individual bubbles and their local mass transfer coefficient. So we have Q dot on a per bubble basis in one individual voxel fluid, that is the neighborhood of fluid that occupies that contains that bubble, for a given species is going to be equal to the convective mass transfer coefficient around that bubble, which would be a function possibly of EDR or flow rate, should we choose it to be. It'll be a function of capital A, not lowercase a yet, capital A, the area of that bubble, and then the driving potential within the bubble versus the aqueous phase. This is familiar except for the capital A aspect to some people, but this we'll come through that. But foundationally, on a bubble by bubble basis, if I have a little bubble here, oopsie, didn't mean to skip ahead. If I have a bubble here and I have mass transfer leaving that bubble, the rate at which mass is leaving that bubble is related to the convective mass transfer coefficient, the area of that bubble, and then the concentration difference driving mass flow. If I sum up all the individual contributions from all the bubbles, then I get the total mass transfer rate from the gas bubbles into the aqueous phase. If I divide that by fluid volume to get a concentration, I could recast this as an area per unit volume of fluid, as it were. So this is represented in moles per second, again, meters per second, meters per second, meters squared, moles per meters cubed, right? You see the dimensional homogeneity here. Meters per second, meters squared, moles per meter cubed gives me moles per second. The sum over all these, moles per second. If I want moles per liter per second, I divide this by system volume, which is why the V gets tucked into the A, and we arrive at a lowercase a, an area per unit volume. But either way, both approaches are fine. And that's how we often think about mass transfer in these bioreactors. Don't forget about the free surface. The free surface is different. It's the same general mechanism, the same general convective relationship, where we have some convective heat transfer coefficient, a mass transfer coefficient, times an area of this interface, times the concentration difference. But here I'm purposefully introducing a different transport coefficient name, H. Okay, more of a canonical convective mass transfer coefficient, as it were. Why? Because it's different. It is a different transport mechanism. A bubble is typically small compared to the Taylor scale. The interface is large. It is a different convective transport mechanism. And so foundationally, they're both convective transport processes, and they both push oxygen into the system, and that oxygen, once inside the aqueous phase, is indistinguishable. But I want to be able to discriminate which is coming from the headspace via this canonical convective transport mechanism, H, and which is coming from the bubbles, which are all called K. I'm not calling them the same thing because they're two different transport pathways. And again, oftentimes people measure KLA inside, well, I'll use that term. We use it so loosely. I measured KLA. No, what you measured was the time evolution of the dissolved oxygen concentration, and you ascribed it to bubbles and then projected it onto a KLA model, which is fine, but your probe may, again, as I've been speaking to, have been adulterated by this additional oxygen transport coming from the headspace, and you're shoving that all in the bubbles when the bubbles may be getting credit for work they didn't do. And that could be a problem when you scale up. Let's speak to that again. Again, let's think about this in the context of a high turn-on bioreactor. The same logic applies. Think of like a low fill volume here, 40, 60, 90 liters in less than an XCR 200 liter vessel or whatnot. Again, in these types of systems, you can have a headspace purge, where you're continually turning over the headspace with maybe laboratory air, nitrogen, whatever you choose, as it were. But you can be purging this headspace. And so you will have some sort of transport across this free surface interface. In addition to that, you will have some sort of mass transfer, should there be sparged gas bubbles, from the gas bubbles to the aqueous phase. Because it isn't just an academic question. This is how we grow cells in production environments. We have headspace transfer, we have bubbly mass transfer, we have a competition between these two, not competition, I should say, a competition / collaboration. They can compete, as I'll show in a couple of slides. Oftentimes they collaborate to inform some effective oxygen transfer to the fluid, but understanding what the ratio of these two components are and how that ratio varies as a function of scale, important. You don't give bubbles credit where bubbles don't deserve credit. So again, when we measure KLA. Well, we're actually measuring something like this. We have some sort of time evolution of the dissolved gas concentration as it converges towards the saturated limit. So we'll probably start by stripping all the O2 out of the dissolved gas out of there by sparging nitrogen and maybe having a nitrogen headspace purge. Then we'll kick on the oxygen. We'll either do this through sparges and we'll have some sort of headspace turnover. And then what we get again is the time evolution of the DO concentration. It's very routine for people to kind of take like the 20 to 80%, like as we do this linear fit of this convergence towards saturation. This is not peculiar. It comes up all the time in the literature. And so we get some sort of effect from this. We get some sort of effective mass transfer coefficient by fitting the linear portion of this exponential of this semi-log plot to the transport coefficient KLA or HLA. And again, if there are bubbles and headspace transfer present, this will involve a convolution of this both. The convolution of both. If there's no bubbles present, it'll just involve the free surface transfer, of course. But again, both processes exist. Now, here's what this looks like in an actual experiment. This is really interesting. I'm going to talk through this plot because there are a couple parts here. Once you see it, it becomes immediately obvious what's going on. Here I'm changing just for a system with no sparged gas, just headspace, guys. Those are the title of the talk. I have headspace flow rate, which is how quickly I'm turning gas over inside this headspace here. And I have this going for multiple impeller speeds. Okay. Now look what's happening here. In this vessel here, let's say at this particular lower headspace flow rate, I am seeing that I have a impeller dependent HLA. That kind of makes sense. Higher impeller speed, more free surface transfer, higher free surface velocity, higher convective mass transfer coefficient. That conceptually makes sense. But what's interesting here is that as I increase my headspace flow rate, my apparent HLA is changing. That doesn't make sense, okay, on its face. Foundationally, if my impeller speed is fixed, which is driving the dynamics of this free surface, you might say, oh, well, the higher gas flow rate might be impinging on the surface. You know, it's not a problem with mixing in the headspace. We looked at that. So what's going on here? If I put a probe inside this vessel and it's measuring different effective HLAs as the increased headspace flow rate for a given impeller speed, bear in mind, and the constant impeller speed implies that the free surface transfer coefficient isn't changing. What's going on here? Well, we're being headspace gas limited, okay? That is, we're not able to supply this liquid with oxygen at the rate at which it wants to transfer across this interface. Saying it's not until we get to like 10, 15, 20 liters per minute that we can actually supply the headspace with enough gas in order to keep this guy and have it converge to an impeller speed independent HLA. And this is an important point. If you're going to measure HLA in a system, you've got to make sure that your source is in fact constant. And this is easy to do for KLA for bubbles because they're always coming in with lab error, pre-oxygen, whatever they might be. But this trend prevails. Look, as I go to my higher impeller speed. Eventually, as I go to my higher impeller speed, I can see that once I get to like 17 liters per minute, I eventually reach a headspace flow rate independent HLA. This makes sense because I have a higher HLA at these higher impeller speeds because I have a higher interface velocity. That means that I have to spend more, I have to turn this headspace over more quickly until I eventually get to a point where my apparent measurements, my HLA measurements, are no longer flow rate dependent. And again, we talk about this in depth in which this paper was published, but I'll summarize this point one more time, is that we cannot claim to be reliably measuring a convective free surface transport coefficient and a convective free surface transfer rate until we can be ensured that our headspace is in fact well stirred, homogeneous, and constant. And if we are not in that regime, we have this very complex convolution of an impeller speed dependent HLA, a mixture dependent concentration, that's a turnover time dependent concentration, which can be messing up our HLA, and our results are not reliable. Okay, we cannot reliably predict a free surface HLA if we cannot reliably control the environment in the headspace. For a system inside a large room, a little bioreactor, easy. For a bagged bioreactor, you use bioreactor, hard. Be cognizant of the fact you need to make sure that your headspace is in fact consistently what you're setting it to be. Because if not, you cannot reliably predict HLA. Because we've got these competing effects of the transfer coefficient and the driving potential. We've got to make sure this potential is constant before we have any attempt to isolate H. And down here, these are adulterated. So the key point is this: you've got to make sure that you are at a point where your freeze transfer coefficients are in fact being isolated from the effects of this headspace mixing. And again, it makes sense that foundationally, the higher impeller speeds, which represent a higher free surface transfer coefficient, put a higher demand on headspace transfer. That is, they're going to require more and more and more gas flow in order to ensure that the transferring effects across the interface are not significantly disrupting the concentration inside the headspace. And again, the purge can fully supply what the headspace needs much more quickly than the interface can suck it across. Okay, which is what we got to test for. I'll give a tease as I'll speak to this momentarily. These dashed lines are what we predict from the simulation using some pretty straightforward convective mass transfer correlations. Now, the code, if we're not considering headspace effects, just predicts one convective heat transfer coefficient. And I'm teasing, I'll speak to this momentarily, which does a great job of converging to what was measured experimentally. But again, this is an important point. For any sort of mass transfer coefficient calculation, you've got to make sure that your driving potential is constant, or else you get this weird convolution down here, which can make for a head scratch. Like, again, look at this down here. Like, how can you say that if I double my impeller speed effectively, or I should say increase my impeller speed by 40%, my free surface transfer isn't changing? It makes no sense. What you're seeing here is the limiting effect, the rate limiting effect of poor mixing in the headspace. So again, understand that, because it matters when trying to predict this transfer rate. Again, now from the simulation standpoint, like, we can try to use this data to understand and develop relationships for predicting HLA. Okay, so we've got a head start here. We don't have to start from scratch. We know from dimensional analysis that there will be a non-dimensional transport coefficient, a Sherwood number, that should be related to some sort of interface Reynolds number and some sort of fluid Schmidt number. The Schmidt number is just fluid properties. Reynolds number is where we're describing that net effective velocity on this interface as it whisks energy away. If we think of this as something of a flat plate, which is an okay assumption for these vessels here, an idea of a 4/5 and 1/3, very common for turbulent flat plate systems, we'll evoke those. The cofactor, we got to figure that out. I'm going to speak to this a couple times. But foundationally, it should be order of magnitude 1.110, should be somewhere around there. We don't know what it is yet, but we're gonna assume 0.2, and I'll speak to that point momentarily. And if we use that 0.2, and again, I can justify that in a moment, we can do a really good job of reproducing the experimentally measured convective mass transfer coefficients at the interface using a semi-empirical theory. And importantly, it's tracking well, both the magnitude and the trend. So I don't think I'll get my hand slapped for using this sort of correlation. I don't think I'll get my hand slapped for using the 4/5 and 1/3 as they come from pretty semi-empirical flat plate theory. I will get my hand slapped for 0.2, but I can justify it here. But the important point is we can conceptually develop a first principle or semi-empirical model that allows us to predict this convective mass transfer coefficient along the interface strictly from simulation. Okay, you use the interface velocity, etc. One interesting point here that was observed inside the laboratory testing, which we are able to reproduce in the simulation as well, is the effective pumping direction of vortexing. I'll show the picture here after I speak to the data. But again, this is related to interfacial mass transfer, is at low impeller speeds. Again, assuming we're at a case where we have well served the headspace, we no longer have those concentration effects. At low impeller speeds, pumping direction has the same HLA. Okay, it's all, up to about an hour, reciprocal hour or so, up to impeller speeds of 60 or so in approximately a linear way. And just to kind of, I'll put a little bird in your ear, like, yeah, these HLAs are on the order of a few, like 1, 2, 3, 4, 5, etc. in these systems. And that may be small, like in a fermentation system, but in a cell growth system, that's not nothing. Okay, like if you're growing these things in an amber 250 to try to develop a broth or culture, as it were, and you're neglecting the headspace contribution to that transfer and putting all the onus on the bubbles, you're probably not characterizing that process well, and you may have a little handicap as it goes to scale up. So again, 2, 3, 4, we'll see some higher values here. They're not nothing. Yeah, they may be negligible in some systems. You got a really high KLA, but they're not always negligible. I'll speak to this point head on here in a couple slides with some data from GE. But either way, so why do we bifurcate here at about 60 RPM? We see this in both the experiment and the simulation. Well, one's up pumping, one's down pumping. The difference is we start to form a vortex. Okay, so as we go through this here, we can see in the down pumping case, we get a little more surface area and a little more, a little higher velocity. And what this means is we get a little more convective heat transfer along this, convective mass transfer along this interface that kind of characterizes this larger leg. The difference isn't huge. This is more scientific than industrial. If you're an industrialist, you probably just draw a straight line between the two and be like, well, it goes from 0 to 2 as your impeller speed goes from 0 to 140 RPM, that this particular fill volume. That's good enough, I'm sure, for a lot of cases. But there is kind of like a little more information to be teased out as we see the experimentally observable and reproducible bifurcation and understand the physics driving it. It's related to the formation of the vortex and the higher velocities realized in the down pumping case. Minor academic point, but interesting that it is reproducible and physically motivated. But again, the headline is this. The real headline is like, you know what? We can get a few reciprocal hours of transfer across the interface as we operate across a range of pretty canonical operating speeds in these high turn down reactors. Okay, so now we published this. It worked great. It's all exciting. But that point two, I kind of pulled out of thin air. All right. What preceded this work was a more, and I wanted to start off with like the punchline. What preceded this work was a more focused investigation into transfer across these lab scale vessels and never to better characterize this relationship here. And for this, we needed a lot of data because if we're going to claim that we can assign a constant value to C, well, we better be able to test that across a wide range of free surface systems, agitated vessels, shaker flasks, deep well plates, etc. So we have to like sample deep wells, microreactors, lab scale reactors, etc., which have a wide range of HLAs. You know, things going from like 28 down to like, sub 1, 0.22. So we've got like a factor of 100 variation in HLA across these systems. And we want to see and in fact confirm that this generalized semi-empirical theory with an appropriate cofactor can reproduce this wide range of realized HLAs. And again, in each of these systems, there's no sparge. There's no sparge line, okay? All of the transfers coming from the atmosphere, all the transfers coming across the free surface, all the transfers coming from the lab air. And so as we get these different sorts of speeds, fill volumes, operating conditions, we get different measured HLAs. And again, if the idea is true, that we can unify these according to semi-empirical theory, then they should collapse onto one data set. So here's what this looks like. Here's like a snapshot of the shaker flask. You've seen tons of agitated vessels in M-Star, as it were. But here's kind of the real punchline here. So here we have HLA for each of the systems at each of the operating conditions, as well as fill volumes for the reactor. Now, this is interesting here. Like if I look at the shaken systems and I change my shaking speed, my HLA gets really high. It's really high because I get a tiny fill volume in a pretty large area. And foundationally, it gets up to, a few hundred reciprocal hours at a reasonable shaking speed. And if I use this correlation with a cofactor of 0.2, it does a pretty good job of tracking that. So again, calculating the interface Reynolds number, which is the velocity interface, the hydraulic diameter of the well, the viscosity of the fluid. Those are, I think, it's a standard description of a interface Reynolds number. I can track that variation, get the dogleg and the magnitude pretty well with a cofactor of 0.2. Let's take a look at the stirred system, which was this was the 15 milliliter amber 15. I don't have a picture of that here. Same logic applies. We have just free surface measurements, no sparged gas. As my impeller speed goes up, I can get HLAs up to 6-ish or so. Not nothing, guys, in terms of a little amber 15. Right? That's not negligible. If my total KLA is like 10, if my apparent KLA is 10 and I'm just sparging gas, I might misappropriate that KLA to the bubbles, give them credit for work they didn't do. and give the free service credit, not give it the credit or accommodation it should have had. I'm not talking about trying to be fair here. I'm talking about if we're misappropriating mechanisms of mass transfer, we're going to scale up improperly. But at the end of the day, not bad. The 0.23, and you might argue, well, you're off, there. Yeah, not bad as I kind of look at this general trend with this one cofactor 0.23. I can look here at my my predicted, this is for the 3-liter vessel. I can operate at different sort of fill levels here. And okay, if I use 0.19 as my C, I can kind of track the results pretty well. Again, here at a few HLA. And if I put everything onto 1, you're going to say, oh, 50%, that sucks. Yeah, it does. But at the same point, I'm going over 2 orders of magnitude. And it's better than 50% for the majority of these. So I think it's pretty compelling to choose a pretty constant cofactor. You might say, well, dude, you're predicting a KLA of 7 when it was actually 5. I'm like, well, dude, I'm going from 300 typical hours to 2 with 1 correlation to rule them all. In a shaker flask, well, agitated vessel, amber 15, and even a production vessel where I use the 0.2. So it's kind of compelling to be able to use kind of these first principles flat plate, I would say semi-empirical flat plate turbulent theory to develop a correlation that works across KLAs ranging from 1 to like 300, as it were, whether it be a shaker flask or whether it be a high turn down bioreactor. And it's very compelling to me that we can get all this data from the simulation because all we need is the specific surface area. That's the area of the interface about the volume of the fluid, and the velocity of the mean velocity of the interface. And that's to derive an interface Reynolds number. And to be able to convolve those into kind of one correlation to rule them all is pretty compelling to me over kind of, again, look at this. It's 2 orders of magnitude with 1 correlation. And that's not just an HLA, it's in volume as well. We're going from 0.2 milliliters to 2,000 milliliters, even up to the larger volumes that I'll show here later of 90 liters. Like, that's cool to have a generalized correlation that spans that many orders of magnitude decades. I didn't mean to be punchy that dude stuff, but it's like I don't mean to be punchy there. But it's worth noting. As engineers, like even like me, I'm picky, but sometimes you got to recognize a win. Okay, now just to be clear, there is so this 0.2 I think is justifiable. Okay, and when I was doing that high turn down bioreactors, it wasn't like, oh look, if I use 0.2, I recover this data. What a lucky coincidence. A lot of simulators do correlation hunting, where they'll like find a parameter that works and then reverse justify. Like, oh, of course 0.2 is the right answer because so-and-so in 1942 said it should. But if I can go and use it and then prove it, and I actually proved it before I used it, that's a compelling argument and be able to get this answer right. Now, let's go back to the actual high turn down bioreactors to understand a bit of what's going on. So, again, we're stepping back to the high turn down system here, using that 0.2 because we believe it's true. If I look at this guy here, some things make sense. As I increase my impeller speed for a given fill volume, okay, my HLA tends to go up. Makes sense. My higher impeller speed gives me higher interface velocity, gives me higher interface convective mass transfer coefficient, gives me more mass transfer. And again, all of these are operating in a case where I have a well-stirred headspace. That's where I hit that point so hard. Because if I did not have a well-stirred headspace and did not isolate the effects of headspace mixed in my HLA, this would be nuts. This wouldn't be trustworthy. When we've gone through the rigmarole of isolated headspace mixing effects to make sure we are reliably targeting HLA. And it goes up. And I'm calling it HLA because it's not KLA. It's a different model and it's a different transport path. Now, what goes on here? As I increase my fill volume, HLA goes down. Why? Well, there are 2 effects. One has a big effect, one has a little effect. First of all, the higher fill volume in principle might reduce the interface velocity at the top of the system. That's not the bigger effect, but that's one possibility here. Because you have more fill volume, there's going to be less velocity at the top. The bigger effect is the fact that there's just more fill volume. So again, A is now a smaller quantity, right? We have the same surface area in a non-vortexing system, our interface area, pi d squared over 4. That's not going to change much as I change my fill volume in the absence of vortexing. But if I have a higher fill volume here, that little interface has to supply a greater volume of water with oxygen. And so foundationally, the HLA, the net transfer coefficient, goes down linearly effectively as my fluid height goes up because I'm depressing the amount of volume, fluid volume, that little interface has to carry. And this goes down as fluid volume goes up because our A gets smaller. Not because interface changed, not even because HL changed that much, but it was because that little interface had to carry a larger volume of water and try to supply it. So as we get up to larger volumes, like 90 liters per so, it's getting down sub 1. And this is interesting because as we change our fill levels here, which it is not it's not earth shattering, but it's kind of obvious after the fact, is that if we're changing our fill volume throughout this process, if we're changing our fill volume as we scale up or scale down, we're going to have this kind of knob here that's changing how much oxygen is actually arriving inside the cells to supplant whatever might be coming from the sparged gas. And again, to argue this point more clearly, yeah, there's a mild effect, certainly raising the fill level, depresses the velocity a bit, but HL is pretty constant across impeller speed and fill volume. Yeah, it's a little lower. I can see that point, a little lower. But most of this change in HLA is driven by A, driven by the increasing V, which drives down A and drives down this entire term. And that's kind of an important point. It's like your HLA is changing over time. You're going to have this kind of like fluctuating bed of mass transfer coming from headspace that you got to be aware of. Okay, and oftentimes these can compete. Okay, so this is really interesting here. Like, let's say I've got headspace transfer with sparged gas bubbles. Okay, and so now if the headspace and the sparged gas are the same material, this gets a little easier. It's not necessary, but if they're the same material, you can solve this really easily. So we know that the mean concentration, let's just ignore mixing effects for a moment, at a given point inside this vessel is going to be related to the HLA, that's the mass transfer from the bubbles, as well as the KLA, and that's the mass transfer of this kind of, the HLA, the mass transfer from the interface, I misspoke there, and the KLA, the mass transfer from the bubbles. If the gas are the same, we can recover an analytical solution. If the headspace is pure nitrogen, for example, let's say that we've got no oxygen coming from the headspace, we can simplify this expression even further to extrapolate what kind of the mean concentration should be. So again, I'll speak to this briefly because I want to get to the working demo. But the key point is this, is like if we have a headspace purge, okay, if we have a headspace purge and we have ongoing oxygen sparge, our realized equilibrium concentration will bounce the transfer of oxygen from the bubbles into the aqueous phase, as well as the loss of oxygen from the aqueous phase into the headspace. And that will greatly depress our mean DO concentration, okay? And so if we don't have oxygen in the headspace, if we strip it out and strip it with nitrogen, as it were, this can depress what sort of DO we're seeing inside this system. Said again, even though we're sparging, we've got our hand over our hearts, and we're sparging our gas, we've got our lookup table, which tells us what our KLA should be, we will not realize this corresponding DO. It'll be way off. Why? Because free surface transfer, interfacial transfer, is hurting us. Rather than putting oxygen into the system, now that headspace is stripping DO. It's stripping DO from the system and stripping it fast. And the more stripping we get, the less this KLA can keep up. The more stripping we get, the more depressed, I should say, our equilibrium concentration will be. And so if we're going to eliminate the effects of stripping due to the free surface transfer, we've got to either make KL high, so this number, that is a small addition compared to this number, so this normalizes to 1, or we need to make HLA very low. That is, use high fill volumes or somehow minimize transfer using other schemes. But foundationally, like again, there's this ongoing competition between the headspace and the sparged gas bubbles. Sparged gas bubbles are present. And if you have an overlay on top of your system, you will necessarily not poison, that's a bad word. That's so like draconian. You will adversely affect, you will kill, no, just kidding, but it will perturb, change, and make your expected DO levels not right, given your expected KL. So you've got two effects here. One, your scale up might have been wrong, so you thought the bubbles doing more than they actually were when you're getting a free surface assist. And then if you have an overlay, then the free surface is coming back to bite. Like now it's taking things away that it was actually helping you with, and your bubbles just can't keep up, and your realized GO is just low. And this is all measured data here. This is not just experiment or simulation. I'll show the simulation next. The simulation was here with some of the measured KLA data, predicted KLA data, but this is a measured effect. This is not just conjecture. Okay, let's talk about why this really matters now within the context of a real kind of experiment here. And again, I love single-use bioreactors. Like single-use bioreactors are how I keep my house hot. Okay, like metaphorically speaking, if you know that reference. I'm not like renting tables at a Comic-Con or anything, but but foundationally, so we have this like good data where it allows us, like Cytiva did a good thing, or maybe GE did it before them, where they kind of provided this nice data where they measured KLA at different operating conditions, and they create these maps. This hand over heart, this is great that they do this. Like it gives people an expectation of what sort of KL they might be able to realize at a certain fill volume, an airflow, and agitation rate. This is cool. Like this is a good thing to do. A lot of vendors, not just in general, like they play coy with their data. So hats off to these guys, like helping engineers make good design decisions. I give them credit. But there's something peculiar here. If we look at this, kind of look at this data. So they're reporting KLA. You can read the report. What they did is they put a probe in there and they measured the time evolution of the DO, like every good engineer will do. But as we discussed today, we're putting all the benefit onto the bubbles. And if we're not accounting for the headspace, this may not be what the bubbles are actually doing. And look at this number for a minute. Okay, so we're looking here at the 40 RPM impeller speed. That's way too low to break up any bubbles. The bubbles are just kind of rising like a bubbler. There's not any breakup going on inside the system. And this is the lower fill volume here, the 15-liter system right here. We see that as our gas flow rate goes from 0.25 to 5, right? That's going up a factor of 20 times as much gas, and no breakup. Bear in mind, it's just kind of like bubbles rising, just in an airlift system. No meaningful breakup coalescence, not enough energy to do it. Our measured KLA only goes up by a factor of like 4.5. Like that's weird. Like, and people are like, oh, well, the bubble's breaking up. Well, no. Let's really tease something. No, I'm not just gonna throw it under the spargers changing. Well, no, let's tease this a bit. Like, why we put in 20 times as much gas and got like a 4x increase in KLA? Like, what's going on? Well, there's actually a lot of Look, let's look at some of the details here. We have 15-liter vessel. That's small. We have a small impeller speeds, not a breakup, but like, is there something going on here? Well, luckily we can calculate this. We now have reliable ways of calculating, at least from simulation, like what this free surface transfer should look like. And I actually got this guy booted up. Like, here's what the system looks like. I just ran this, just kind of have something to show. Like, here is what this reactor would look like in the simulation, okay? These are all operating the downward pumping cases for the G spec. So you got gas bubbles coming up. There's no meaningful breakup of coalescence because, quite frankly, there's just not enough impeller speed to break the bubbles up. We just got bubbles coming out, as it were. We have a free surface there doing its thing. Free surface is kind of bouncing around. And if we look at this guy here, we can see that the free surface certainly has some sort of velocity, right? If I go to this guy here, like there's a velocity there. So I can calculate, what the Reynolds number of this free surface should be. Certainly, if I go back to this guy. So there's my free surface buzzing around, getting a little bit of a vortex there, right? Kind of watching that guy just have a day. There's my free surface swirling. So I can calculate here what my interface Reynolds number should be. Like I can calculate, for example, from the simulation, like exactly what that interfacial area is, as well as that this is the mean velocity, as well as my interfacial my area, as well as my mean velocity. This precesses around like 0.08 or so. But foundationally, so from a simulation, I can extract out like what my mean velocity is of the area of that interface, as well as the mean velocity, as well as the area, as it were. As I mentioned, I've got a pretty reliable correlation, at least one that spans a couple orders of magnitude on HLA to try to predict what this actual corresponding free surface transfer coefficient is. So I'm going to use 0.21 because I got it on good authority. It works pretty well. I've got this is actually a little bit higher. So double check my math, but it's fine. This is actually a little bit higher. I mistyped that number in there. It's like 0.08, but you can do the math. I've got some mean interface velocity. I've got a diameter here. I'm sorry, I did goof up a lot here. This annoys me so much. I just got to fix it. That diameter here refers to the diameter of the vessel, which is 0.3 meters, just for those keeping score at home. And this mean velocity was something like much closer, like 0.08. Sorry about that, guys. I goofed on that slide. This reflects the diameter of the vessel. There's a viscosity or diffusion coefficient of the gas. And so foundationally, we can arrive, and we also know the specific surface area that comes from the area divided by the volume. We know we can use the simulation tool to predict and extract that the actual HLA for the system is going to be about 0.6 reciprocal hours. Okay, like that's not nothing. It's small, but it's not nothing. And so, okay, so what we know inside the system is like there's probably some physics are not accounting for. That is, their 0.8 is likely a 0.6 from the headspace, which means that the bubbles are probably only 0.2. And remember, the interface speed is not going to change dramatically with impeller speed. And so our HLA is still going to be 0.6 at the higher gas flow rate, implying that our KLA is probably going to be around probably about 3.7. And now these numbers make a lot more sense. Okay, if I add 20 times more gas flow to this particular system here, like I would expect a number somewhere around 4. Okay, recognizing that my free surface transfer coefficient, the 0.6, was giving a huge assist to what was being contributed by the bubbles at this lower gas flow rate. And here it's less of an effect, it's less of an assist, but still noticeable. Where there's two kind of key trends here. One, like, yeah, it didn't make sense, and it doesn't make sense that if I increase the gas rate by a factor of 20, that I get 4 times more KLA. Why? Because the measurement I hypothesized, and I think is pretty compelling, was convolving the free surface with the bubbles. And what this means is that if I go back to this guy here, this is probably not particularly trustworthy, at least in this corner down here. And again, nothing but love for effects. I think it's great work. I'd love to do this. But to be sure, this isn't KLA anymore. This is an HLA-dominated physics. And again, we kind of mask that with the color scale. We go 7 down to like something below 7. But to be sure, deconvolving this into its constitutive components and being able to see how those components come together to give rise to this aggregate value, very useful. Not only for kind of deconstructing the transport pathways, but also understanding how those adverse effects scale up and the physics of each. And just to be sure, I'll kind of show this guy here. Like you can do all this in one. Like here I am, if I kind of look at this guy, like I've got, my system spinning. I can see, for example, that I've got, I'll color this, not by velocity, which is interesting, but that's not what I want to see here. If I color this by DO, like I can see kind of these effects. I'll choose a better scale here to make this a bit more pronounced. So I can see like early on, I'm getting like, you can see some of the oxygen being whisked away from the bubbles, as it were, which is great. You can also see some of the oxygen kind of coming in through this headspace up here. You can see some of that up there. That's not only being mixed, but being transferred from the headspace, and see the convolution of the two. And so if I want to kind of, I'll just let this guy run and accumulate. So I'm seeing like oxygen accumulate inside the system. Some of it's coming from the bubbles. Some of it's coming from the headspace, as it were. And so if I go in here and look at my DO concentration, my scalar DO, like this can't discriminate between the two. It just sees the two pathways, unless, of course, I actually look at this guy and see what my free flux is in moles per second and see what my scalar coupling rate is in moles per second. Then I can begin to compare these guys more empirically. And this was the higher impeller speed case here. But here I see that I'm getting about, for every, let's just say 4.5 moles of oxygen coming in from the bubbles, I'm getting about 1 mole from the headspace. Not nothing, as it were. So as I kind of watch this guy, you can see the oxygen accumulate and begin to deconvolve those two. And just for those keeping score at home, I did kind of wire this up to define global variables, which allowed me to compute like my HLA inside the code. I'll show that momentarily. This is just some bonus material for those that know and use M-Star. But the actual code looks like this. I'll jump over to this and I'll close out and take questions, of course. But the code looks like this. I've got, familiar old KLA down here. Nothing new here. I've talked about this ad nauseum in previous talks. I love my constant KL. Fight me if you don't like that. And I'll use breakup times. These are all reasonable values. And now here's how I'm doing my free surface transport. I'm doing an HLA calculation. So like I'm just doing this on the fly. I'm calculating my interface Reynolds number using my interface velocity. I'm calculating my Schmidt number. I'm calculating Sherwood. I'm dimensionalizing it, and then making sure I can calculate HLA. HL times interface area divided by fluid volume, converted into hours, reciprocal hours, as it were. And how am I doing interface velocity? That's just like a global variable. I'm taking the mean of the interface velocity as we're directing them stats. Interface area, pulling it into the code. Tank diameter, that's the set value. Fluid viscosity, that's just set to fluid viscosity. Diffusion coefficient, set to diffusion coefficient. Fluid volume, set to fluid volume. HL, HLA being calculated as part of the script. It all comes out. And then I also have here inside the DO an interface flux. I've got a headspace concentration, and drum roll please, here it is, HL, headspace concentration minus local DO concentration. There it is. It's just as we had it scripted up on slide 2, where we talked about these mechanisms of transport. So again, I can deconvolve them, see the pathways, see how these all come together. Okay, let me go back to these slides here to kind of carry out and go back over here. Sorry for jumping around. I know these presentations can be nonlinear, but they're interesting, hopefully. And just to be clear, one comment on this AI, just so folks understand where it's coming from. The red values are coming out of the code. Okay, the code, we already determined what these parameters should be. That's the vessel diameter. These are physical properties. The code isn't figuring out what the viscosity of the fluid is. These are input parameters. The code is figuring out the velocity of the interface. The code is telling us the specific surface area. And these inputs ultimately derive via the correlation and via the definition of HLA, what the HLA is. Okay, what the HLA is. Okay, conclusions. Interfacial transfer among free surfaces is really interesting. And I think it's like an underappreciated science that I think strongly influences process scalable and process design. I think it punches above its weight, especially certainly in shaker flasks where there's no bubbles, as it were, but even in sparged bioreactors. If we're at a lab scale or higher turned down environment, we will get a non-trivial contribution to that transfer across the interface. If we're trying to characterize it, make sure your headspace is well stirred. I really hammered that point with those kind of 3 plots converging with increasing gas flow rate. Go back and watch the tape if it was a point you want to see a bit more. But to isolate the free surface transfer effects, you've got to make sure you have a reliable driving potential. And do that, you got to make sure you're in an open lab, you have a very well stirred headspace if it's a bag. But again, I said an HLA, and quantifying it is important because we oftentimes put value and benefit on the bubbles when they did nothing to deserve it. It was all the HLA carrying the water. No pun intended. This is harder to do an experiment than a simulation. In simulation, voila, we got a correlation. We can look up the velocity, get the interface area. We're done, as it were. In an experiment, you have to be very mindful of kind of monitoring your apparent HLA as a function of headspace flow rate. So simulation is a better approach, I think, in this way, especially since it's so well validated. As I showed here inside the simulation, it's easy for us to extract what the free surface transfer coefficient will be using data that comes right out of the code. And these are fast-running simulations because all we need to get here is a steady state velocity field along the interface. We can get that in just a few minutes. It doesn't take long. Once this interface converges to a steady state value in terms of area and velocity, we're done. KL is going to be constant. KL locks in, as the word. HL locks in. And to be sure, we can then see the pathway. So if we had no sparged gas, the only oxygen source would be free surface, of course. We can then see how it's mixing and going throughout the system. We could also, if we wanted to inside the model, color these. We could have oxygen 1, oxygen 2, and kind of see where oxygen the headspace got to, where oxygen for the bubbles got to, and see if there was some sort of a disharmony between how they were mixed. I don't think that would happen, but you could do that. Then you sum them together when doing sort of reaction kinetics. But to be sure, you could do these as 2 different species and kind of have purple and yellow oxygen and seeing what ratio of oxygen from what spot. That'd be kind of academic. It would be interesting. Lastly, we compare the ratios of each source term. And this matters. This really matters because, quite frankly, we've got to understand if we're going to successfully scale up this ratio right here. we've got to know what fraction is coming from the bubbles, what fraction is coming from the headspace. In some cases, especially for that GE case, these were flipped. I think a majority was coming from the headspace. A fraction was coming from the bubbles. And not understanding that deconvolving that can lead to poor scaling. Okay, great news. We have time for questions. I think it's the first one we've actually time for questions. Okay, Amber, I'll put it back to you. We did better today. We actually got time.
Yeah, this is good. Yeah.
We did a good job. Okay, let's pause for air, take questions, and yeah, thank you for your attention so far.
Since we have an extra moment, I just want to take it this time to draw your attention to these beautiful images, these CFD images that we've used to promote these webinars and on this webinar to populate these slides. Over the last year, they have all been created by our colleague, Johannes Wutz, who is with us today. He's based in Germany. And we're just so grateful to him for his creativity and artistry. And I just want to take a moment to point that out.
Yeah, they're beautiful. It's like, it's rare to find smart people that are, well, a smart person that's really good at like art is an incredible person, okay? Like you can find a lot of dumb artists. You can find a lot of like brilliant physicists that are drawing stick figures. But like to have the both, that's a special person. But
so big thanks to Johannes. Big thanks to Johannes. But we do have a few questions, so let's move on to that. First of all, can we get bubble size and bubble size distribution throughout the system? Also, can we get whether the system is flooded or not?
Yeah, of course. And so just to be sure, if I go to the system here, this didn't have any breakup to speak of, but there may have been some bubbles that had underwent coalescence or whatnot. So if I go to something like this, and let's just do a little bit of cystics here. Let's go to my particles and see like, okay, yeah, there's a little bit of, this might be pressure related. They might be expanded as they rise, but let's just take a look at this. So there's a little, they came in at 6 millimeters, which is what was kind of absorbed from the spargel. But and there was a little bit of, so maybe there's a little bit of coalescence events. Let me just look at the size distribution. This won't be very interesting because there's so few bubbles, but I'll do a histogram just to see, like based on the diameter, like there's just a little bit of variation, Like there's just not that much. I don't have any bubbles here. This histogram is going to be kind of poorly populated. But yeah, you get some that coalesce up to a little bigger, about a centimeter or so. Some that you got one small satellite at a millimeter, but a majority of them are coming in, are as they came in. Maybe a little coalescence. Again, this is an underwhelming bubble size distribution because I only have like, how many bubbles? I have 250 bubbles. It's not very much gas transfer in the system. But if we have more bubbles, these histograms can become much more complete. Flooding, yeah. Flooding is often characterized by changing the power number, an abrupt change in the power number. We've spoken about that a lot. If you want to reach out, I got slides I can send you and some presentations we've given. We're characterizing flooding in different impellers. But yeah, size distribution, flooding, that's all good.
Okay, we have another question coming over from the Q&A. Was the effect of the HLA studied experimentally for a stirred vessel without any sparger or bubbles?
Yeah, lots of times. So if I go to this over here, and this is the point I was trying to make here. These were all and I think the question was there no sparging, right? Was that the question? This had no sparging.
Yeah, was the effect of HLA studied for a stirred vessel without any sparger bubbles?
Yes, yeah. This is all without sparging. And this picture could have been better because there were no gas bubbles in this case. So I tried to use my hands to pantomime, my words to yell. But this had no sparging. And so as a consequence, all this HLA we're seeing, all the DO we're seeing, all of this here is coming entirely from the headspace. And so, yeah, in fact, the only case I had with convolved sparging and free surface transfer were these examples here, where I spoke about when they compete. And these guys, when they measured this was both sparging and headspace transfer. We didn't do that until we had both individually characterized very well. Good question.
Okay, next question. Can bubbles be generated from the surface vortex shear and generate bubbles by entrainments of top airspace?
Yeah, this is routine. We've given a couple talks on this. I don't know if Eric Jans is here. I'm not going to put him on the spot. I'm not going to even bring him up. But either way, it's like he's talked about things like self-aspirating impellers at AICHE. And I think we've got some neat work to actually maybe formalize about that. And so that's an extreme example, but to the person asking the question, it is the exact same physics. is getting an interface down, in this case, down a shaft and outside the impeller blades to be cut up. Yeah, we can do that. And by induction, we can certainly do a vortex coming down and being ripped apart to form individual Lagrangian bubbles. And we do have Eulerian Lagrangian coupling that allows us to look at how once a free surface breaks up and once it forms into bubbles, how those bubbles then further break up or buzz around the system as Lagrangian point objects.
Okay, next question. How do you compare DO measurement from sensors, which is relative as percent, and the absolute DO concentration from CFD simulation?
You just divide it. Like here's an example. Like it's all the time people do stuff like this. Like here's a case. Let me just sanitize this name real fast. But it's just a normalization. Like the same way the sensor does it in some sense. Like it just normalizes by what the okay, just 1 second here. I just wanted to get this. Okay, here we go. So like it's not uncommon. Like I have a local variable here called sat percent. And it's just like I'm dividing the local DO concentration, which in M-Star is moles per liter, by the saturation limit, which I knew just from hand calc would be 0.3 moles per liter, just based on the, I assume, 21% oxygen and air at STP. But it's, yeah, you can divide this and present not just moles per liter, but actually like sat percent at different locations across the, which are oftentimes a more organic way to look at this data.
Good okay, question. Our last question. So what's the recommended agitator type for gas liquid mixing? Is it pump down or pump up based on your simulation results?
Well, I mean, it depends on your application. I mean, in these, it depends what you're trying to accomplish. In these high turn down bioreactors, if you're looking at scale down process or a turn down process like this, there's not going to be a big difference because yeah, there'll be a slight, you know, maybe 10% variation in HLA depending on impeller pumping direction, but it's not going to, it probably is not going to swing the ship one way or the other. So yeah, in high turn doesn't make a huge difference, as it were. In other types of systems, the pumping direction may inform blend time. So that's something to consider. But for HLA in a high turnout system, I don't think pumping direction has that big of an effect. But there is an effect, but as I kind of claimed when speaking to the slide, it's kind of more into academic than industrial. And I think if most people were looking at this and they're in a, you know, manufacturing facility, they just do that and be like, you know what, that's our mapping. And yeah, there is some nuance there between these guys, but that's probably, that uncertainty is probably lower than the uncertainty set the system, such as like, how did the cells behave that day? And the viscosity of our glucose mixture that we didn't characterize. So yeah, I don't think it's a big influence there, at least in what I've presented.
Well, that wraps it up for our questions, and we are, we've reached our time.
Yeah, email if any questions come up. Thank you so much for your attention. Be well.